Section 2, zero input data structure. Zero input data structure is very similar to NASTRAN. It consists of 3 sections. The first one is called executive control section. The second one is called case control section. The third one is called bulk data car section. And before we talk about the input cars, we have to define so-called set for structural and aerodynamic models. For structural models, if we say G set, now G set means 6 times number of grid points in the structural model. This because of each grid, structure grid has 6 degrees of freedom, and in terms of T1, T2, T3, R1, R2, R3, and those degree of freedom are defined in the local coordinate system. If we say A set, that means analysis set. A set is the number of degrees of freedom by excluding SPC, MPC, O set from the G set. If we say H set, that means number of structural modes. For aerodynamic model, if we say J set, that means the number of aerodynamic panels or boxes. If we say K set, it's 6 times J set. For displacement, each aerodynamic panel has 3 displacements. In terms of H sub X, H sub Y, and H sub Z, and its displacement along X, Y, and Z directions. And the 3 slopes is partial HX by partial X, partial HY by partial X, and the partial HZ by partial X. That means the slope of the 3 displacements with respect to the x-axis. Why we only need the slopes along the x-axis? Because in the boundary condition, only those terms appear. For aerodynamic forces, each aerodynamic panel has 3 forces, namely Fx, Fy, Fz, and 3 zero moments. If we say C set, that means the number of aerodynamic control surfaces. In the executive control sections, and we have the required command is called assign FEM. Assign FEM imports the structure finite element model solutions, and we have another required command called CEND. And this one ends the executive control sections. This is a typical example of the executive control section, and we have assign FEM equals, and we have a assign matrix to import a matrix, and then we end this executive control section by CEND. The assign FEM equals command is a required one, and at least one assign FEM equals command must exist, but no more than 2 can be specified. The assign FEM where A you specify the file name of the structural file element output file, and form equals you specify what kind of a file element solver you use. And the boundary, what's the boundary condition to generate this model solution? And you have print option. You can print the file element model solution in the output file. And you have a support equals, and this one tells ZAERO how many rigid body modes in the file element model solution. And you have a set equal to yes or no. So the example, you have say assign FEM equals to equals demo S dot F06, and form equal to MSC, boundary equal to SYN. That means that this mode is a symmetric mode, and support equal to 135. So you have a 3 rigid body symmetric modes, and if you have anti-symmetric, you say boundary equal to anti, and support equal to 246. And for NASTRAN, when you run NASTRAN, you must have echo equal to sort or both, and you must use solution 103 to generate the model solution. And also in NASTRAN, you have option. You can generate the mode shape at a set degrees of freedom. In this case, in the NASTRAN input file, you have to say S vector equal to all. Or if you want output the mode shape at a G set, then you have to specify displacement equal to all in the NASTRAN input file. And when ZAERO reads the final element solution, it also reads the final element input data to specify the grid point and the coordinates, natural frequencies, and generalized mass, stiffness, and mode shapes. ZAERO does not need to know the connectivity or property cost of the final element model. So you can use the following NASTRAN command. Say when you run NASTRAN, you say echo echo equals sort parenthesis core 1C 1R 2C 2R 2S comma grid and S point. So you only ask NASTRAN to output the input output those input costs. Okay, and so if you want also area elastic analysis to another party, okay, but meanwhile you don't want to give out all of the information of your structural model, and so you can use this statement in the NASTRAN, and then with this statement, the output file generated by NASTRAN will not contain the connectivity and the property costs, but this output file still can be processed by ZAERO. Another thing, if you say S factor equal all, and in the A set degree of freedom, and if some of the grids if it's non-A set degree of freedom, but meanwhile it has mass attached to it. Okay, so in this case you're gonna miss some masses, and therefore the initial load calculated using this S vector equal to all may not be accurate. And this is a typical NASTRAN solution 103 output file, and so it sort you print out the solid Bode car, and followed by the eigenvalue, generalized mass, generalized stiffness, and eigenvectors, which are the modes. In the entry form in the assigned FEM, specify what kind of a file element solver that generates the structural output file. So if you say form equal to MSC, that's for MSC NASTRAN or NX NASTRAN. If you say NE, that's for NE NASTRAN. This is for SOs, that's for SOs. If we say ideas, form equal to ideas, that's for ideas, also can be generated by ANSYS. If you say form equal to abacus, it's for abacus. If you say form equal to Altair, is for Altair. We also have a free format options. Okay, so if you look at the menu, then you know what's the format of the free format option to import the structure model solution. And so these days, the final element model become bigger and bigger. So sometimes when ZAERO reads in the final element output data, and if the final element model is very big, it may take some time. So if you don't change the final element model, when the first time when you run ZAERO, and in the bulk data card section, there's a bulk data card called FEM save, and you can specify a file name to save the imported model data. The next time when you run ZAERO, you can say form equals acquire. Then in the entry, the file name will be the file name you specify in this FEM save. So in so doing, you can accelerate this importing process. And the entry boundary, you have three options. For if the final element model is a half-span model, you may have a so-called symmetric mode for symmetric boundary condition. You may have an anti-symmetric mode for anti-symmetric boundary condition. If you have a full span model, you have to say ascent in the boundary. Okay. Of course, the specified boundary condition will affect the downstream displays such as flutter and trim. Now, if you say ASAC equals yes, then in the NASTRAN analysis, you have to say S factor equal to all. Okay. And then in the assign FEM command, you have to specify entry ASAC equals yes. And the entry support equal is an optional input to specify the degrees of freedom of the rigid body mode. So you say support equals 1, 2, 3, 4, 5, 6. That means you have a 6 rigid body mode, and it is always encouraged to specify support and whenever you have a rigid body mode in the finite element model. Also, if you say support, if you put a negative sign in front of the integer, for example, support equals negative 1, 2, 3, 4, 5, 6. The negative signs trigger out ZAERO to perform following tests. The first one, you will replace the input rigid body mode by the ZAERO internally computed rigid body mode. And this rigid body mode is in the so-called body axis. And for the pitch mode and yaw mode, the rotation center is at REFX, REFY, REFZ, defined in the car called ARZ car. And so there are many reasons, and it is always highly encouraged to specify support equal to negative, then followed by the degree of freedom of the rigid body mode. Okay, we will talk about why we need that in the later sections. And another executive control command is called assign matrix. You use this command to import a matrix in the output for format. The output for format is a standard format of NASTRAN to store a matrix. Okay, and again, you specify assign matrix equals the file name. You have a option called form, and you have an entry called mname, and you can specify print. And why you need assign matrix command? Because if we want to compute the inertial loads, and sometimes you have to import so-called MGG. MGG is a GSAT mass matrix, and then for the form, you have several options. You use if it's a form equals format. That means the file contains non-sparse and ASCII format. If you say format 23, it is also non-sparse and ASCII format, but with the D23.6 format. If you say on format, it's for non-sparse and binary format. If you say form equals S form, that means sparse and ASCII format. And recently, we add the option. Now, the assign matrix can import the sparse and binary format matrices. And you have to specify the M name, okay? And where you give a name to the matrix, okay? And there are several hardwired matrix name in ZAERO. MGG, whenever ZAERO sees MGG, it understands that this is a GSAT mass matrix. So this is a typical output for format of a matrix. And if you want to output a GSAT mass or stiffness matrix from NASTRAN, and this is the NASTRAN DMAP altered statements. And for example, if you say output for MGG, and then you output the MGG matrix into this file called demo.mgg. It is formatted and non-sparse. If you want to output ASCII and sparse matrix, then you put a negative sign in front of the 12. So the 12 uh, 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 matches this guy. And for binary and non-sparse matrix, you have to say form equal to unformatted. And for binary and sparse, you have to put a true here. And why we want to import the GSAT mass matrix? Because we want to compute inertial loads. And to compute the inertial loads, you have to use a sign matrix and give a name called matrix name called MGG. And so MGG is a program assigned matrix name to store the GSAT mass matrix. So therefore, whenever ZAERO sees a matrix name called MGG, it understands this is a GSAT mass matrix. And how ZAERO use MGG to compute the inertial load? Because the inertial load equals the MGG times the acceleration at each structural degrees of freedom, and x can be represented by a mode shape times the generalized coordinate. So x double dot equal to phi s times c double dot plus the control surface acceleration times a control surface kinematic mode, and this kinematic mode is generated internally by ZAERO. And sometimes we also in the closed loop ASC state space equation, we need a matrix called MHC. MHC is the inertial coupling matrix due to control surface diffraction. We call phi c, and multiplied by MGG and pre-multiplied by the mode shape transpose, and that give us so-called MHC matrix. Is the initial coupling term due to control surface diffraction. And also from the MGG, we can compute so-called the KGH matrix, because this is the eigenvalue problem of the finite element solver to solve the natural frequencies and also the mode shape. So this tells us the MGG times the mode shape pre-multiplied by the natural frequency square, which is a diagonal matrix, equals to KGG times phi. So KGG times phi we call it KGH, and this one is called omega n squared times MGH matrix. And once we have a KGH matrix, whenever we want to compute the grid point force, and we can multiply the KGH matrix to the generalized coordinate solution. And this method is called mode displacement method. So therefore, we do not need to import the KGG matrix, because KGG matrix sometimes could be very, very large, whereas MGG matrix usually is a highly sparse matrix. And other executive control commands include GenGAS. Whenever you want to perform a gas analysis, you have to specify GenGAS in the executive control sections, because if you specify GenGAS, ZAERO will generate a gas ASC, and then with the gas ASC, you will compute the gas so-called the gas column. Okay, and another command is called solution, which is quite useful. And if you say solution -1, and it stops the program execution after the aerodynamic panel model is generated, and and then you can quickly use a card called plot error card to look at your aerodynamic panel model. Okay, and if you say solution -2, you stop the program execution after the spline module is complete. Then you can use a card called plot mode to verify your spline input. And because if you don't specify solution -1 or -2, The next module will be the UASC module. Once ZAERO gets into the UASC module, it computes the ASC matrices, and for large aerodynamic model, it could take a lot of time. So you want to use solution -1 and solution -2 to verify your panel model input and your spline input. And another one is called sub AC50. And after solution after ZAERO version 8.4, we move the control point, the force point from the 50% core to quarter core. Now, if we want to roll back to the earlier solution of ZAERO, you can specify sub AC50. So you will move the force point from quarter core back to the 50% core. The next section of ZAERO input is called case control section, and you have you can specify a title and echo. Okay, echo means you want ZAERO to print out the input file, and then you can specify many sub cases, and each one you start with a subcase equals. Okay, and then you can specify a subtitle. You can specify a label within each subcase. Then within each subcase, you select engineering discipline, and then you to generate a particular aeroelastic solutions. And you end the case control section by the begin book command. In all ZAERO input, if the first column is start with $, that's a command statement. So ZAERO will not read this line. And for the disciplines, we have ASE, AFL, A flat plan, and DFS, ELOs, and so on. So we have many disciplines you can specify within each sub case. And this is a typical example of the case control section. And you have title, you have echo, you sort. So ZAERO will sort the input cars and print out in the output file. And then you have two sub cases. Then you end this case control section by begin book. And within each subcase, you can select a disciplines, flutter, trim, ASC. And if you for example, if you specify flutter to 10, then you must have a bulk data card called flutter with ID 10 in the bulk data section. And if you specify trim equal to 110, then you must have a trim bulk data card with ID 110 in the bulk data card section. And in the bulk data card, each card has 80 columns, and it divided into 10 entries. So each entry has 8 columns, and all the input card, the bulk data card input section begin after the begin bulk case control command, and you must end the bulk data card section by end data. Okay. And then for each card, you specify the name of the card, and if the input entry exists, if one input card is not enough to specify all the input data you need, you have to use so-called the continuation card. And then in this entry, you say plus A, and this entry you specify plus A. So you understand this line is a continuation line of the first line. You also can leave plus A and plus A as a blank. So blank with blank, they match. So ZAERO also understand the second line is a continuation line of the first line. And then you have another option to specify a bulk data card, which is called free format. So you only separate entry by comma. Okay. And the interrelationship of the module showing in this slide. So you start with a high fidelity geometry module, and you use you import the finite element model solution, and you generate the ASC matrices, and you go to the spline module to interpolate the mode shape from the finite element grid to the aerodynamic panel model. After that, you can select a discipline, and each discipline can generate some graphic file, and then you can use commercial graphic software to view the solutions.